Deep in a canyon in California, the thrust of a rocket engine is tested. Power for a trip far above the Earth. Near the Arctic, in a western desert, technicians prepare to launch a sounding rocket that will broadcast back high-altitude data unobtainable by instruments on the ground. Above New Mexico, a rocket camera records the view as Earth, clouds, and ancient concepts fall behind, giving way to a new picture of man's planet and to a new world of science made possible by rockets. Man lives just above sea level, but above him is another ocean, a sea of air, which dims his view of the vast space beyond Earth. He has always dreamed of reaching out into this space and understanding its nature.
Legend says that human flight began with Daedalus and Icarus. Daedalus flew successfully, but the sun melted the wax on his companion's wings, and Icarus fell. Centuries later, Leonardo da Vinci began to turn legend into science. He designed a vertical propeller to lift a flying machine. In the 18th century, planning turned into actual flight. Man began to take the measure of the strange world above. He found that air pressure declined, while winds and cold and the range of his eyesight increased.
By the mid-20th century, man climbed higher still, learning more about the atmosphere around his planet, extending his reach from a few thousand feet to 100,000 and more. Here, balloons and planes approached their limits. For above 25 miles, the atmosphere is too thin to support a balloon or feed a plane's engine. To explore deeper into space, a new research tool was needed, an engine that could operate without air. The tool was developed based on a natural principle and on an invention older than any plane or balloon, the rocket. The rocket principle is illustrated by the squid, which propels itself by ejecting a stream of water. In the same way, a toy balloon ejects compressed air. When such streams are expelled, there is an equal but opposite reaction, causing a thrust forward. Sir Isaac Newton stated this principle in his third law of motion. To every action, there is always opposed an equal reaction. But man, without knowing it, had already put the principle to use long before Newton's time. 2,000 years ago, the Greek philosopher Hieron developed a revolving sphere, an early reaction engine. In ancient China, the legendary Lord Wan Hu used rockets to take off for outer space. He may still be there. Rockets were also employed in battle, as well as public celebration. In the early 20th century, pioneering amateurs experimented with rockets in several parts of the world, especially Germany. rocketry advanced more quickly after scientists such as Tsiolkovsky in Russia, Aubert in Germany, and Goddard in the United States turned their attention to problems of theory and practice. Goddard was the first to achieve high speeds and altitudes with liquid-fueled rockets. Goddard showed that the rocket could be used to explore the high atmosphere. The Germans in World War II were the first to use a rocket engine in an operational plane, a 600 miles an hour Messerschmitt Interceptor. The Germans also produced the first great stabilized modern rocket, V-2. Its 14 tons climbed 60 miles and reached targets 200 miles away. The V-2 was a weapon, but scientists soon recognized its great possibilities as a research tool. In America, after the war, captured V-2s carried instruments 100 miles high to measure the upper atmosphere. A V-2 was also used with a Wac Corporal rocket to form the first two-staged rocket system. Greater altitude was reached than ever before, 242 miles. V-2 experience produced the Viking and other rockets, specially designed by American scientists to explore high altitudes, more stable, reliable, and efficient. Today, giant rockets are powerful enough to place satellites in orbit. Other rockets are small and economical enough to serve as tools for many kinds of special research.
What is this scientific tool? A rocket is a tube. It contains a supply of fuel, alcohol, kerosene, or more complex liquids. It also contains an oxidizer, such as nitric acid, to burn the fuel even in airless space. There's also a chamber in which the fuel burns, and a nozzle through which the violently expanding gases are expelled. Some rockets use solid instead of. The small space in the sounding rocket's nose carries a variety of scientific measuring instruments, depending on the rocket's assignment.
These instruments are designed in greatly reduced size, miniaturized, to save every possible ounce of weight and inch of space. They must be extremely sensitive, yet rugged enough to withstand fantastic forces of acceleration and vibration as the rocket gains speeds of over 3,000 miles an hour. They must also be able to withstand spinning, tumbling, and extremes of temperature. Before a rocket can be delivered from the laboratory to the launching pad and put into the air, hundreds of mechanical and electronic parts must be checked. Solid-fueled rockets like this one must be guarded against premature combustion. Rockets are often used in combination. Here, the first stage, at the left, will lift the entire system about 20 miles above the denser atmosphere. Then, miles after the first stage has dropped away, the second stage, at the right, will fire and speed through thin, relatively resistance-free air up to 100 miles above the Earth.
Roger. Telemeter. Roger. Telemeter 2. Camera 1. Camera 2. Radar 1. Roger. Number 2. Roger. Number 3. Roger. Stand by. Minus 25. Minus 25.
Just before the rocket is fired, instruments on the ground are set in motion to record its flight and signals.
Minus 15. Minus 10. Minus 10. Minus 5, 4, 3, 2, 1, 0.
A sounding rocket's destination is the vast region of the upper atmosphere. What is this region like? What happens here? How does it vary? How is it different from the lower atmosphere?
First of all, only within the bottom 3.5 miles of the atmosphere can man breathe without oxygen equipment. 90% of the atmosphere by weight lies below 10 miles. The temperature falls about 1 degree Fahrenheit every 300 feet until it reaches minus 80 degrees about 8 miles up. The whole region below this level is the troposphere, where almost all weather is made. In the next dozen miles is the stratosphere, relatively cloudless and calm. Here the temperature rises sharply. 99% of the atmosphere's mass is underneath. The pressure is so low that man's blood would boil if he were unprotected. Above the stratosphere stretches the middle atmosphere to a height of about 50 miles. Here it gets much colder again, dropping as low as 117 degrees below zero. Extending from 50 to many hundreds of miles is the ionosphere, electrically charged by radiation from the sun. At a height of about 60 miles, the air is only 1/1,000,000th as dense as at sea level, and at 100 miles, 1/1000,000th as dense. Above the Earth's atmospheric blanket, man has no protection against tiny meteorites, cosmic particles, or invisible radiations from the sun. His voice would not carry. He would be cooked during the day or frozen at night. Because there is little air to reflect or react to the sun's rays, man would see no blue, no weather, no clouds, mist, rain, or snow. And above the distorting atmosphere, the stars would look smaller and their light more steady, burning like hot coals in the universal black.
Today's sounding rockets, such as this small 5-stager, or the rockets that were used during the International Geophysical Year, generally climb almost vertically 60 to 500 miles into the upper atmosphere. Their total flight lasts only 8 or 10 minutes. How do scientists keep in touch with the rocket during this brief but crucial time? Through an incredible variety of electronic devices and techniques.
Plus 25.
To track the rocket's progress, they use radar and radio.
Plus 50.
316.
To obtain the information recorded in the rocket's nose, they use two basic techniques. In some cases, the instrumented nose cone may be separated from the rocket, as in this shot, photographed from the cone itself. With its speed retarded by parachute, the nose cone falls toward Earth, as in the case of the Jupiter rocket instrument package shown here. The cone is reclaimed at sea or on land, its data recorded on film or magnetic tape. Data are more often obtained by telemetry. Inside the rocket, measurements are converted into electrical signals, which are radioed back in code to the Earth. The code uses variations in the length of the signals, the time intervals between them, and their frequency. The incoming signals are recorded on tape and then interpreted in the laboratory. What do such signals reveal? Already they have provided a great amount of information which was unknown a few years ago. Information on the forces in the upper atmosphere, radiation, particles, and the magnetic field. Information on the atmosphere's composition, structure, temperature, and density. How are rocket experiments conducted? How, for example, does a rocket determine the range of density of the upper atmosphere?
One technique employs a small metal globe known as a falling sphere. The sphere is ejected from a rocket at a high altitude. Its instruments measure the rate at which the sphere slows up as it falls into denser levels, where there is increasing atmospheric resistance or drag. From the time the sphere is ejected, it transmits these measurements continuously to ground receivers. Falling sphere measurements give a profile of atmospheric drag and thus atmospheric density at all levels through which the sphere passes in its brief fall. Experiments like these have resulted in startling discoveries. For instance, density measurements made 120 miles up have indicated that it is much hotter at times over Arctic Canada than over the New Mexico desert. Rockets have found many such variations at different times and places in the upper atmosphere.
To measure winds as well as temperatures high above the Earth, rockets may be equipped with grenades. These can be exploded up to heights of about 60 miles and still be clearly heard by sensitive microphones on Earth. Much above this level, there isn't enough air to transmit sound adequately. As the rocket climbs, each grenade is ejected and exploded in turn. The explosions are timed by radio, and their sound is picked up by microphones. The scientist measures the interval between the radioed time of each burst and the time its sound reaches the ground, 4 or 5 minutes later. With these facts, he computes the temperatures of the different layers of the upper atmosphere and the speed and direction of high-level winds. Rocketry offers new research possibilities of special interest to the meteorologist. Confined in the past to local weather observations, he has long needed a tool which would give him a panoramic view of cloud formations and storm patterns that spread over hundreds and thousands of miles. Instrumented rockets and satellites have this ability. Such rockets as the Aerobee can be equipped with many different kinds of cameras as well as other sensing devices which produce photographic information. Taken from an Aerobee 100 miles above New Mexico, this picture combines many photographs from a rocket camera. It reveals cloud formations stretching over thousands of square miles. Even more remarkable, it shows the birth of a cyclone, invisible and unsuspected from the ground. And it shows how man can detect and track storms long before their destructive forces go into action. With cameras, falling spheres, grenades, and other ingenious devices, man is adding new and significant details to his picture of the upper atmosphere. Probing even farther, rockets are sending back facts about conditions and processes in near space, especially in the ionosphere, where thin gases are electrically charged or ionized by X-rays and ultraviolet radiation from the sun. The ionosphere is essential to man's worldwide communications because it reflects all his long-distance radio signals. By penetrating right into the ionosphere, rocket instruments provide new knowledge of the radiations which are absorbed at these heights, and so do not reach instruments on Earth.
Not only do rockets transmit direct data on these radiations, they also give scientists an indirect portrait of their source, the sun itself. In exploring the complex relationship between sun and Earth, rocket soundings are particularly important when unusual solar events occur. During a total eclipse near the Danger Islands in the Pacific, clouds hampered ground observations, but did not interfere with research by rockets. Special detectors were designed to record ultraviolet radiation and X-rays from the sun. Rocket soundings made before, during, and after total eclipse all recorded X-rays. But when rockets passed through the moon's shadow, they recorded no ultraviolet radiation. This suggested that ultraviolet comes mostly from the sun's face, which was hidden by the moon. However, X-rays were recorded all through the eclipse. Thus, they may originate not only on the sun's face, but also in its corona, visible throughout the eclipse.
In this way, rocket soundings added to our knowledge of the sun, its radiations, and their effect on the ionosphere. They have also begun to produce a more exact portrait of the sun itself. This photograph was taken from a rocket above the atmosphere's distorting effects. It shows, in ultraviolet hydrogen light, more details of the sun's hot and cooler gases than have ever been seen before. Rocket soundings have also aided the study of particles, such as cosmic rays, which stream through space toward Earth, from the sun and beyond. These particles can best be studied in their original state, in the high upper atmosphere and beyond, because form secondary particles. Among the tools that measure primary cosmic radiation is the rockoon, combining the rocket and the high-altitude balloon. The balloon carries the rocket nearly 16 miles up, well above the denser part of the atmosphere. Then the rocket is fired. It will climb over 75 miles farther into space, much higher than if fired at sea level. Its payload includes a Geiger counter, photocell, and ionization chamber to record the cosmic bombardment in detail. Such probes tell us that cosmic ray intensity is much greater near the magnetic poles than at the equator.
Thus, new facts are gathered about the basic relationship between particles from outer space and the Earth's magnetic field. Due to its location in the North Magnetic Pole region, Fort Churchill, Canada, is an ideal place to study cosmic rays, and particularly the awe-inspiring aurora.
The aurora, shown here in time-lapse photography, occurs when charged particles streaming from the sun come into contact with the Earth's high atmosphere, causing its rarefied gases to glow. The paths of these particles are controlled by the Earth's magnetic field, and so they tend to concentrate near the magnetic poles. Up to a few years ago, the aurora could be measured only from the ground by visual means or radio telescope. But recently at Fort Churchill, rockets have been fired right into auroras, measuring the electric currents present and reporting the energy and character of the auroral particles. Aurora, the magnetic field. Cosmic rays, radiations from the sun, all are related. And rocket firings, sometimes coordinated in many countries around the world, are probing these relationships. What of the future? Satellites and spaceships will reach farther into space, but scientists will always find use for the sounding rocket, whose province is the atmosphere, where no satellite can last. Research by rockets, a young and exciting scientific technique, will continue to open new windows, allowing man to see and know as never before his planet Earth and the space beyond.